Okay, so I guess we can start. So today is our last lecture before the student presentations. So I will finally give a proof of identification for Poisson boundary, and in fact, I will present my recent work with the Farhani, Frisch, and Chawla, but then in fact I will only focus on the case of hyperbolic groups. The general case of group actions on hyperbolic spaces is quite similar. So to avoid a few technicalities, we will focus on the hyperbolic groups case. So what is a theorem? So we let G a one hyperbolic group. So it's Gromov. And mu is a measure on G, a probability measure such that to simplify things slightly, the support generated by the semigroup, so the semigroup generated by the support is the whole group. In fact, now we can even relax it to the group generated, but okay, that's a minor issue. And so we have to assume a certain thing about the measure. So hyperbolic, okay, and also G. Okay, so if G is Z is a hyperbolic group, then the Poisson boundary is either trivial or we know when there is drift what it is. So that's kind of not so interesting. So we could say non-elementary. So okay, let's say if G is not virtually cyclic, and the entropy of mu is finite. So that's the only condition. Then yes, the Gromov boundary delta G mu, so with the heated measure, so the heated measure is mu, which we know exists because we proved last time the convergence theorem for random walks on spaces and groups acting on hyperbolic spaces. So if the group is hyperbolic itself, means the Cayley graph is hyperbolic. So is a model, it's isomorphic, it's a model for the Poisson boundary. Of G. Okay, so let me recall that this theorem. So note that okay, so the above version is recent, but well, there's an earlier version which is when we also have logarithmic moment. But if with finite logarithmic moment and addition, it's been known by much longer time. So by Kajmanovic in the for hyperbolic groups itself, even already in the 90s, 93. And for groups acting on hyperbolic spaces, then well, that is the work of many people with the log moment. But so, and also the second note is note 1, note 2. So the same thing extends. So same is true if G is a group of isometries on, again, a delta hyperbolic metric space and then we have the two conditions. So, and okay, the first condition, we want that, yeah, the mu is non-elementary. So mu is non-elementary, meaning that the semigroup generated by the support of mu, which for instance is G, is acts with at least two loxodromic elements. So this means there are two independent loxodromics, but and also that we need one more condition, and again, G contains at least a WPD element. So the support, the semigroup generated by the support of mu has to contain at least a WPD element. So we need certain properness, even if the space is non-proper. But this is somewhat the minimum level of properness that you can get in some sense. So it's really, it's quite satisfactory. So,
okay. Do you assume that here G is discrete or finitely generated or anything like that?
Countable.
Okay.
Yeah, the support of mu could be anything. Yeah, could be any countable set. Yeah, whether there's a version of this for locally compact groups, it's a good question. I think there should be a similar. Yeah, I think that, yeah, if you maybe add a few more conditions, I think you should. There could be a version of it actually. But yeah, other questions? So yeah, so in particular, why the second is interesting is more for geometric group theorists or people interested in applications, because yeah, the groups acting with the WPD element are many more groups than just hyperbolic groups. For instance, relatively hyperbolic groups, right-angled arcing groups, mapping class groups, out of n, and so forth. So this applies to large class of hyperbolic-like groups. But for the purpose of the proof, I think it's plenty to just focus on hyperbolic. Okay, so actually, let me start with a toy model where the proof is somewhat not that technical. And the toy model is when the group is free. And even when the group is free, in fact, in this generality, the theorem was not known. So there is some new idea in the proof. So for the toy model, let's say that G is a free group on, say, two generators. Let's do that. And in fact, yeah, even more than that, we want the semigroup. So we want that, let's suppose, so F2 is generated by A and B. And in fact, let's even suppose that the support of mu is not the whole group, but it's in a semigroup, in the positive sub-semigroup. So basically, we can say, suppose that the support of mu is contained, or the support of mu is contained in the positive semigroup. So AB semigroup. So why do we care about this? So well, that eliminates a lot of the trickeries about the random walk, backtracking, and stuff like this. So what is the picture? The picture here is just of a binary tree. So that's the Kirigov of, so X here is just the Kirigov of the free group or the free semigroup with standard generating set. And yeah, so we know it's a binary tree. And what does it mean? So yeah, so we have choices A and B, right? So we can go right or left. So we have A you go right, for instance, and B if we go left. Classical picture. And so why is it useful and nice that the measure is supported on the positive semigroup? Well, because it means that, yeah, you never backtrack on this tree. So what are types of words, right? So types of words could be A, so you go one step to the right, or B, you go one step to the left. But you can have much more complicated words because, yeah, you can go like, you can do A, B, A, for instance. That would be another word that you can do. Yeah, you have a countable set of words. So this is not necessarily finite. If it's finite, it's much simpler, the whole story. So, but since this group is, since we have a free semigroup, when the convergence property really is trivial, the random walk will obviously converge. Every path will keep going forward, so we will go towards this boundary. So since let's call this F2 plus. Yeah. So since the support of mu is contained in F2 plus, every path converges. I guess almost, we can say almost every, because, okay, the only thing that could bother if we allow for a lazy random walk. So if you can stay at where you are with certain probability, well, okay. Then maybe one path is excluded, the one for the path where you go somewhere and then you stay there forever. So okay. But almost every path converges to the boundary of X without any backtracking. So it's much easier to control the trajectory of course. So what do we want to prove? Well, the Gromov boundary of this object, well, what is the Gromov boundary of this object? Well, obviously this is an infinite binary tree. So the Gromov boundary is this Cantor set at infinity of rays. Right. So this is Cantor set. And so we want to show that this Gromov boundary, this Cantor set with the Heaton measure, which is given by doing the random walk here, is the Blossom boundary. So, and now if you recall, we did the theory, the general theory of Poisson boundary. So we know what is that we want to prove. So we want to prove that for almost every point, so you pick a point psi in this boundary, and we want to say that if you take the random walk and you condition on hitting this point on the boundary, then the entropy of the rock, which is conditioned to hitting this point on the boundary, is 0. So by the entropy criterion, so that's why we need the finite entropy actually. So we still apply the entropy criterion, like Kaymanovich, but then the next step we apply it differently than the classical. So the entropy criteria says for nu almost every boundary point, the relative entropy is 0. So what is the relative entropy? Well, if you recall, it's basically entropy of the n step of the walk conditioned at hitting psi at infinity. So it's the entropy of what I think I called mu star n sub psi something over n. So this is the limit. This is the conditional entropy. Meaning that, yeah, we want to show that, yeah, if you take all the paths that converge here. So how come is there more than one path that converges here? Well, what do we mean by a path, right? So this random walk never backtracks. So it will stay on this geodesic forever. It will start here, will stay on this geodesic forever, but it can travel along the geodesic at different speeds. So there will be different paths, as in the sense of the timing of the paths will be different. So they all lie on this geodesic forever in the story model, because everything is just there's no backtracking at all. But already even this is not completely trivial. Because again, the support of mu could be infinite, and estimating this entropy is not so easy. Are there any questions on the setup? Yes.
I'm not sure what you mean by the different speeds at which you can travel along the geodesic.
Yeah, you can, because so let's make an example. Let's say that a support of mu is a squared b, a cubed b squared, a cubed b squared, something a 1,000 b. So there's there's infinite many options.
So what step is like?
Yeah, each step is in the, yeah, for instance, the first step, maybe the first step could be this, or maybe this, or maybe that. So the first step already you could have comfortably many choices for the first step. So that's the difficulty, because yeah, again, if the support of mu is finite, well, then this problem is much easier. I agree, because you can only go this far after n steps. So, but otherwise, that's what makes this problem. Okay. So, other questions on the setup?
But it seems like even with the finite moment condition, it's still like because you still can go far for first step. So it seems like even to not be trivial there, right?
It's not trivial. It's a theorem that has been cited many times before ours. Yes. Sure.
Okay.
Yeah. I mean, of course. In fact, what I want to say is there's still an open problem here that we do not know how to solve. So if we remove the entropy assumption, even for this binary semigroup, we don't know what the boundary is. So because then it becomes extremely hard to control this relative, like, yeah, there's no good, you cannot really talk about this relative entropy. It's not even well defined. So if you take any measure, so of course that's the natural conjecture that given any measure on the semigroup on two generators, the only possible Poisson boundary has to be the scatter set. I mean, this is what else? I mean, the question is, do you have to record more information than that? Well, it's hard to imagine that there would be a bigger boundary, but we don't know. So this is in fact very hard problem if we remove every assumption. So the entropy, finite entropy assumption tells you that we can still apply the finite entropy criterion. in the relative form. Okay, so how do we do this? So the idea is, we come up with this general method, which we call the pin down method, or pin down approximation. And I mean the thing is, this to be compared with the classical theory was this ray approximation or strip approximation. So if you have a moment condition, then you know much more about the geometry of the walk. You know that after some number of steps, well, the probability that the walk is too far towards the boundary is kind of negligible. And that's very useful. But since we don't have any moment condition anymore, we have to modify this. And so this is what we call the pin down approximation. So in this case, it's relatively simple. But okay, this is the general statement. General statement is this lemma. Okay, so we define two types of partitions. So so recall that, so let AN be the partition of omega, which is again the space of infinite sample paths. A good friend from earlier parts of the course. So AN is the classical partition that we use to compute the entropy. And how is that defined? Well, such that you have a path WK is equivalent in this AN partition to WK prime if they're the same at step n. So if WN equals WN. So this is the information that you gain by knowing at the end step where is the walk at the end step. And so, of course, so recall, so you note precisely the following, that indeed this conditional entropy, which I think we called H peak psi, this conditional entropy is nothing else than the limit of the entropy of this partition AN, because this tells you that location of WN. So it's like taking mu n star here, the end step of the walk, given psi over n, where psi is the geometric partition given by the geodesic. So means what? Means what does the geometric partition means? Means that Wn is the same in this psi partition to Wn prime if, well, the limit Wn equals the limit of Wn prime in the boundary. So this is the partition that we know it gives us this geometric boundary. So we split the whole space of paths according to where we end up. So this is and we know this is a mu boundary. And so what we want to know is we want to know that once we are given the information that the random walk converges to, say, to psi or to wherever it converges, how well can we tell where the end step is? So that's the game, information game. Okay. So this is a good partition, but now the pin down approximation tells you the idea is what if we can add a little more information? But of course, we have to be careful. We cannot add too much more information. And so we say the following. So let Pn, we add some other sequence of partitions, a sequence of partitions, again, of the same infinite path space. And if, so there's two things that has to be checked. So the first one is that for almost every boundary point, say in boundary, the limit as n goes to infinity of HAN, but now we add a bit more information to the prior. So we add this Pn. So Pn is something else that we can measure of this walk. So we add this to the prior, and we add the knowledge of where it converges. Suppose that we know that adding, so this means we add a little bit of information to what we already know. And suppose this is enough for us to kind of tell us where we are at step n. However, we want also something else, which is, well, we don't want to add really too much stuff. If we add too much stuff, then, I mean, of course, you know, Pn could be just a trivial partition. We know exactly where the whole path. Okay, that this would be true, but of course, this would not be helpful. We still want to say that what we add is not too big, too much. And so the second thing is to say that if we take the entropy of Pn globally without any condition, you divide by n, yeah, this is also going to 0. So the amount of information that you're adding globally is still negligible, it's still not. So if we know this too, then, well, then we can tell that the boundary is the Poisson boundary. This is a general principle. The proof is quite simple. So it's just basically the property of information, right? So what do we want to show? So we want to show that this is going to 0. So we want to show that h of an given psi is going to 0. Well, what we can do, again, we can add, yeah, we can add p. So we can do, yeah, we can do Pn given psi. So we do this experiment, Pn, we give some information. And then, okay, if we want to know HAN, so, well, now we have done the experiment, so we put it in the prior, we put it in what we know. So this is the classical definition of conditioning. We're just conditioning on adding this other thing. And now, the only thing we have to see is what? Well, this is the relative entropy. So we know that by convexity, the entropy of Pn condition at psi is bounded by the global entropy of Pn plus this. So again, this is an exercise in entropy or information, but it's like the intuition, I think, should be clear. So and then by 2 we know that this is small o of n, and by 1 we know that this is o small o of n. So it's small o of n. Okay. So this is just a general statement. Now, how do we apply it to the toy model? So that's why I wanted to present the toy model first, because it's kind of it's much simpler to see whether yeah, with the toy model. So you have the story model. And so the situation is like this. So what do we need to show? So I've given you a point psi on the boundary. So this forces the walk to move along with geodesic, even though maybe at different speeds. And now, what else? So what do we want is, can we give more information so that we can predict? So can we predict the end step of the walk? So how can we predict the end step of the walk, right? So I know that I'm traveling along the street. What other thing I have to tell you where I am? You can probably guess, right? I mean, I know that I'm on the street. What else do you need to know where I am? The number? No, I mean, just looking at the picture. So how about I tell you just the distance from the origin? Suppose I tell you the distance from the origin, then for sure you know that, well, suppose I know that the distance is 2, well, I know I'm here. Because, right? So once you tell me the distance of the origin, in this case, everything is completely determined. That is, right? So in this case, so the idea here is the following. So what is Pn? Pn is the partition where we partition it for each k, where we say the omega such that the distance between the end step of the walk and the origin is k. So in the language of partitions, I guess you partition the space of paths by this k. And so this tells you the distance from the origin. And now we have to prove the following 2 things. So the first thing we have to prove is h of an given Pn and psi is small. In fact, it would be enough to say that it's small o of n. Well, in this case, it's much, much better than small o of n. Because, again, if I give you psi and I give you the distance, then there is no choice. There's only one possible choice for Wn. It must be that Wn is here. That's right. So if I tell you that the limit of Wn is psi and the distance between the origin and Wn is k, well, this tells you Wn is whatever it is. Basically, we take the geodesic psi and you restrict from 0 to k. I mean, you just go up to step k. So in this case, this one is not just O of n, it's 0. I mean, there is only one choice. There is only one choice for Wn. So this is completely easy in this case, but then the second thing is slightly not completely trivial, because again, this help may be too much. So what do we want to show? The entropy of Pn. The question is the additional information that we added too much, or does it have 0 entropy? So how to think about this? Well, the way to think about this is the following. So we start with F2 plus, this positive semigroup. And we can map on Z, or in fact, even on N. If I map on N in Z by just doing the distance function from the origin. Right? So, and now what? Now, if I take a measure mu on this positive semigroup, so what is really nice about the distance function for the positive semigroup, which is not true in general for a group, is that the distance function is a homomorphism. Yeah, this is very special about this distance function. So note that the distance function d from f2 plus to n is a semigroup homomorphism. Because I cannot backtrack. So the first step, I got distance 3. The second step, I got distance 2. And the distance just adds up. There is no negative. So this is, of course, very particular to this case. But in this case, it's much easier because then I start with the random walk on mu, driven by mu on this one. And if I consider this projection, I get literally a random walk on the integers. So if I project, I consider theta, which is the push forward is star mu. So the projection onto n is a walk, but in this case, it's just really a random walk because this is a semigroup homomorphism. It's not a different type of process. It's completely just a random walk. And so if you think about it, what is Pn tracking? Well, Pn is tracking the projection onto n, the position under this map. So it turns out that the entropy of this Pn partition, so telling how distant the n step is the same as doing the n step of the induced random walk on n. This is literally true in this case because this is a homomorphism. And now we are in a good situation because this is a random walk on n or z. So what do we know about random walk on n or z? What do we know about the Poisson boundary of such a random walk? It's trivial. That's right. So and again, this is a good reason to assume that h of mu is finite. In fact, we need even slightly less. If h of theta, so h of theta is the entropy of the induced walk on n by taking the distance. So we're taking a random walk on the free semigroup, and we're looking at the distance from the origin. And again, the nice thing is this is literally semigroup homomorphism. And so the induced random walk on n has some entropy, which has to be less or equal than the entropy of the original one, just because this is a factor map, so the entropy can only go down. So even for the n step, okay. And so if we know that the entropy of mu is finite, then the entropy of that is also finite. So that's good. And moreover, we know that the entropy of theta star n divided by n, well, this one goes to 0. Why? Because the random walk on this induced semigroup has trivial boundary. So the entropy criterion, you can also do the computation on Z, you just do the computation, but in any case, this has trivial boundary because the random walk on n has trivial boundary. So we do need one assumption, which is that the entropy of this projected walk has finite, because otherwise we cannot apply if and only if. The walk always has trivial boundary, no matter what the measure is, but you cannot interpret this in terms of entropies. Entropy could be infinite, and then it's really completely really unclear what. Okay, so that's basically the proof. So right, because now the entropy here is 0, so the original entropy also divided by n goes to 0. And so by this pin down lemma, the boundary of x with mu is the Poisson boundary. Okay, so this is the case, the sort of the simple case of the free semigroup. Are there any questions? So clearly the pin down method would still work in principle, but what does not work is this part. Because even for the free group instead of semigroup, well, this is very much not true that this is a homomorphism. And so controlling the entropy by just taking the distance is tricky. And the other issue is the random walk can backtrack. So even the step is also not completely clear. And the reason is that, you know, the walk can backtrack. So okay, I tell you it ends up here. And now you can do all sorts of strange stuff before getting there. So how much control do you have on the end step? Well, you see, even if I tell you the distance, well, it can still be in many places. Especially if you don't have moment condition. So the original idea was if you have moment condition, well, it has to stay within some sublinear distance of this point of the geodesic, and so you you would have an entropy bound. But if you have an infinite moment, then it's really impossible to tell the location, the geometric location of the random walk. So that's kind of what we have to give up. Okay, so now in the last 10-15 minutes, I will give you a sketch of the more general case. So the more general case means that we have to add, like, to track more stuff or different stuff instead of just the distance from the origin. And to do that, so one thing we need is this pivoting theory. So Vivian will give a presentation about it. So we will only recall the main, very brief things that we do need. So the general case. Let's say that G is word hyperbolic. And okay, in fact, even the definition of pivoting in general is a bit longer, but let's write down what is the idea. So the idea of pivoting times is the following: that the random walk ends up in some psi in the, so this is the boundary, and well, again, you have this limiting geodesic. So basically, a pivoting time is, so the walk can backtrack and do stuff. But what is a pivoting time? Pivoting time is a time where the walk is close to the geodesic. And moreover, from there onwards, it only gets closer to psi. So basically, if you draw the shadow at this point, the walk later on always lies within this shadow. So Wn, so basically we say that, okay, there are some constants to be fixed, yeah. But basically we say that Wn is a pivot, and n is a pivoting time. If so basically the distance between W and O and this limiting geodesic, so let's call it gamma. Gamma is the limiting geodesic, is bounded by some C that you can choose at some point. And moreover, for any k bigger than n, Wk lies closer. And what does closer means? It means it lies in the shadow of Wn. So for instance, if we have Gromov product, we could say, for instance, that the Gromov product of Wk psi from 0 is bigger than the Gromov product. Yeah, that's one way of saying between W and or if we can say also another way of saying it is that the projection of Wk to this geodesic, let's say that like that. Let's go Pk. Say Pk, which is the projection of Wk onto gamma, lies in Wn. Let's say that. So all the time it's kind of going towards closer to psi than before. It does not backtrack afterwards. So there is a important point that pivoting times exist. I mean, because otherwise this would of course not be theorem. So, and this is due to Guzel. So so there is a difference, which is pivoting time in finite time and pivoting time in infinite. Then this would be the definition of pivoting time in infinite time. So anyways, I'll tell you later what is the exact lemma that we have to use, but this is an idea of Guzel. To use this to study properties of random walks on groups acting on hyperbolic spaces without any moment condition. That's important. Okay, so first let's construct the partition. So how do we construct Pn here? And so to construct Pn, we have to use certain, we have to use these pivots. So we have good times and bad times, basically. So we fix, some alpha, which is some number that eventually will become big. And we denote ik alpha. Well, we pick the interval from 1 to n, and we put it into chunks of size alpha. So ik alpha is the kth one. k minus 1 alpha k intersect 0n. So we're chunking the time. And we say the following. Yeah, we define pivotal times like this. So for k less than n over alpha, so we want to say that in this interval of time, is there a pivot or not? So we denote pk, wpk, the first pivot for pk in ik alpha, if it exists. So we're chunking like sort of the time of the walk. So, well, you think about like something like this, and now this is in the space, but you think that okay, that there is an interval in time, so the walk does something at some point. The first time that you are in ik alpha, at some point maybe you see a pivot. So if you see a pivot, you record it. You call it wtk. So tk is the time. And maybe there is no pivot. And so if there's no pivot, yeah, you don't do anything. So at the next time that you're in this interval, maybe there is another pivot. So this is wtk plus. And so we record this tau, which depends on n and alpha, which is this tau 1, tau n over alpha. So these are pivotal times. And so this is one thing that we have to record. So remember, before we only had to record the distance. Now we have to record three things. So the first thing is the pivotal times. And the second thing is, how about the distance between pivots? So we have to do some sort of distance. And so if we are in good time, so in the sense that there is the pivot, then we can measure the distance. In fact, suppose that there are two consecutive pivots, wtk plus 1. Then we can measure the distance between them. So we define the good distance. So d n alpha l. Oh yeah, and there's also another, there's also another parameter l. So we say k is a good time if good interval if there is a pivot in ik alpha, and moreover, not just there is a pivot, but the distance at each step is not too big. And yeah, so the distance between wj and wj plus 1 of the walk is less than l. L is another parameter we have to choose for every j in this interval. So the good time means there is a pivot at some point, and also every step is not too large. It's bigger, it's smaller than certain L. Again, L will be chosen carefully at some point. And then we do measure this distance, which is in the good times, we can measure the distance between consecutive pivots. So basically we have dn alpha L, which we call it the good distance, so to speak. And the good distance is like that. Well, you measure the sum of the distances between consecutive pivots, pk plus 1, where you assume that ik alpha and k plus 1 alpha are good. So we are assuming that there are pivots, and we can measure the distance. So the idea is that this is like the original case of the semigroup. The walk is going in the right direction, so we can track its progress just by measuring the distance. What is really ruining the party is that sometimes the walk is not going in the right direction. And so these are the bad times. And for the bad times, we have to measure, we have to keep track of something more. We have to keep track of everything, actually. So that's the kind of annoying part. So the bad times is B, we call it B and alpha L. So these are called the bad intervals, or bad times. So for those, well, in this case, we record everything. So we record G, J, G. Yeah, so for each one, so we have to record everything. So we record G, J, G, J plus 1, blah, 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 up to G, J plus alpha for each J, which is the bad time. So it's a lot of things. Basically, every time you're in a bad time, for instance, here there is no pivot, and here you have to record everything, meaning you have to record each step, not just the distance, but really each group element, what each group element does. So this is a lot of information. It's linear, and that's bad. But what saves us is that these bad times are sort of rare. So that's the usual idea. And in fact, so the critical lemma, which comes from this Gozell estimates of pivoting, is the following, is that for any delta, there exists some alpha, such that for every alpha bigger than alpha naught, there exists some L, okay, okay, sorry for that, such that the probability that IK alpha is a bad interval, so there is no pivot, or either there is no pivot, or there is some step which is too long, well, this is less than delta. So somehow you can pick it uniformly. So you can choose this, you can put this scale alpha big enough so that you see the idea is intuitive. Like if I pick a larger interval, it's more likely that there is a pivot. So that's kind of not complicated. But what is subtle here is the uniformity. That basically this alpha only depends on delta. And so that's where we use this Gozell PUT. Okay, and so just to putting things together, once you have this, then we are in much better shape to define our partition. So as you could guess, we can define this this pin down partition as the union of all this information. We put P and alpha, so we record the pivotal times, we record this good distance, and we record these bad times. So that seems like a lot, but fortunately is still okay. That's the point. So yeah, so at this point it's clear. So we need to do two things, and then I'm done. So if you want to know that if you add all this information, suppose you add all this information and you add also the place where you're converging at infinity, well, this really pins down more or less pins down the path. And again, what is the idea of reconstructing the path? Well, the idea is I've given you what are the pivoting intervals. So you know that, okay, this is good, and the other ones are bad. And you know that, yeah, you know how much progress is made between pivotal times. So between pivotal times, you know how much progress is made. And outside of pivotal times, well, how much progress is made because you're measuring the sum of those distances. And then in the between, well, you know the whole path, so you can reconstruct the distance because you do know the whole path. And so the only thing that is left is to show that this does not add too much entropy. So, and what is the idea here? Well, the idea here is that h of, tau and alpha, including d and alpha L, including b and alpha L, is O n. And again, what is the idea here? Well, you have to be careful with the estimates, of course. But roughly, what is the idea? Roughly, the idea is, okay, the distance is a number, and is a number big at most L times n. So this entropy is basically at most log of Ln, which is small o of. So this ones, so we have to keep track of n over alpha numbers, which are these pivotal times. But each number is not too big. Each number is, yeah, there's alpha plus 1 choices for each such number, because this is an interval of length alpha. And if there is a pivot, it's one of the alpha options. So there's, again, so this is log of alpha plus 1. And now this is the bad stuff. So the bad stuff is indeed bad, as the name suggests. But in the end, yeah, in the end, this is less than what? Yeah, I mean, this is less than 3 epsilon times n, basically. So we pick the epsilon at the beginning, or maybe this delta. Yeah, basically this delta. The epsilon is more or less this delta. So we pick this at the beginning. We choose everything else. So the fact that the intervals are bad is small, and how many intervals where there's at most a linear number of bad intervals. Well, not linear, but linear with a coefficient that is small. So this, because of this. Yeah, I guess, yeah, to make it simpler, I think let's call it delta. Right? So there are at most delta times n intervals. And so the total entropy is delta times n. And so, yeah, if you take this, of course, yeah, if you do this, if you take this and you do 1 over this, and you do the Linstrup of this, well, this is less than log alpha plus 1 over alpha plus 3 delta. And so by taking alpha very large and delta very small, we can play this game. So we can make this. Let's see. So okay, so this is the technical part. So I think I'm definitely over time, so I don't want to burden you anymore. But the basic idea is this, that again, you have these good intervals and you measure the distances in the good intervals, and this doesn't have much entropy. And the bad intervals, potentially, they have lots of entropy. But by the pivoting theory, they happen quite rarely. And so that's why, in the end, the total entropy that they carry is still small as compared to 10. So that's okay, good. So I think that's the end of the course. Thanks for your patience so far. Good. Are there any questions, comments? Why is there? Well, this is already exponential. Like, I mean, the thing is, yeah, you have n independent events, or epsilon. It's like you have epsilon times n independent events. So So the total entropy is already the sum, yeah. That's right. That's right. Yeah. Okay, good. So see you next week.